Okay, so guys, there's one other thing you need to grab. You need your AP equation sheets. Do you guys need one? Anyone? They're free. Just printed them. Spencer? There you go. Come on, Max. Let me give you one. There you go. Ronnie? Oh, it's totally up to you. Come on. You do. Do you need one, Leslie? Gage, you need it? You're good? Okay. Okay, so guys, open up your AP equation sheet to the thermochemistry, the thermodynamics side, page 4. And then, guys, if you would please open your books to page 801. You guys all set? Okay, so let me explain to you then, guys, the way that the way the rest of the day is going to unfold. So as a result of our previous combination, guys, you have some interesting ideas in your head. One is that entropy is really a thing, that disorder is not some abstract idea that's just nice to think about. Guys, entropy is a driving force in our universe. There is an energy associated with disorder. There's an energy associated with entropy. And that energy, remember, energy is the ability to make a change, right? So guys, that energy, that entropy energy can cause things to happen. Well, guys, what we're going to do first is we are going to take entropy out of the abstract and we're going to quantify it. We are going to put units to disorder and we're going to do some calculations. Then, guys, once we're done with that, we're going to talk about Gibbs free energy. Now, guys, Gibbs free energy, you're going to find out, is a blending together of Chapter 5 and Chapter 19. Chapter 5 was all about endo and exothermic and enthalpy. The beginning of Chapter 19 is all about entropy and disorder going up. Well, guys, Gibbs free energy then is the bringing together of entropy and enthalpy. And again, as we said last time, this is the only determinant of whether a process is actually spontaneous. We said that all spontaneous reactions give off energy, right? Yes? Well, what kind of energy do all spontaneous reactions give off? And the answer is Gibbs free energy. It's not necessarily heat, it's not necessarily disorder, but it is always necessarily Gibbs free energy. And so, guys, this then provides the outline for today. Number 1, we're going to quantify entropy. Then, guys, number 2, we're going to talk about Gibbs free energy. We're going to bring entropy and enthalpy together. And then we are finally going to be able to answer the question, is this reaction spontaneous, and under what conditions will that change? Guys, that's our day. You ready to go? Goes like this. So first of all, we got to talk about quantifying entropy. And guys, you have the notes in front of you. You don't really need to worry about these first ideas, but we can talk about them. So guys, when we talked about enthalpy changes, we said that what we do is we actually measure change by knowing where something started and where something goes, and we do that by tracking temperature. Well, guys, when we talk about entropy, we do not talk about change. So the idea is this. So we have we'll say this metal block, and we said that there's no way for us to know how much enthalpy this has, right? We can't stick an enthalpy meter in here and measure enthalpy. So how do we know the enthalpy of a block is changing? What do we actually see change? The temperature. But guys, we can actually measure entropy. We don't have to talk about entropy change. We can actually measure the entropy of this block. Now, how do we do it? Well, there's things that we need to know. We need to know the mass. We need to know the crystal structure. We need to know the temperature, things like that. But guys, we can actually give this a number. This block has this much entropy. Now, the question is, what are the units for entropy? Well, guys, if entropy is an energy, what do the units have to be? Joules, and they are. Guys, this is what is called standard molar entropy, and it is measured in joules per mole Kelvin. You may want to write this down. So, guys, joules is energy, right? But what is the amount of disorder for a system dependent on? Well, first of all, moles. Doesn't that make sense? The bigger your bedroom is, the more messed up it can get. Yeah? If you have a small bedroom, there's only so messed up it can get. Well, guys, that's true here too. The more of something you have, the more messed up it can be. But then, guys, also temperature. Messed up is also a function of temperature. The hotter something is, the more messed up it is, because hot things wiggle faster and that makes them more messed up. So if you really want to make a mess of your bedroom, earthquake. Shake it. Never mind. Because that's really what temperature does. It shakes things. Come on. It's an analogy. Not a very good one, but it's an analogy. All right, so guys, this leads us to some guidelines. Remember when we circled disorder 11 times? Circle this one 12. Guys, this is critical. I'm telling you right now, this is critical. Do you all hear me saying this is critical? Because 50% of you are going to miss this question on the test because you forgot this is critical. Guys, this is the Achilles heel that the AP authors are going to go after with a knife when they try to trip you up on these questions. So, while yes, we can quantify entropy, there are some guidelines that you need to know. Guys, first of all, this. Elements have entropy. Remember when we talked about the idea before that the heats of formation for the elements are 0? Well, guys, that is not the case here. Elements have entropy. That makes sense, right? Energy is not required to form them, but they do have disorder. Then, guys, this. Circle this one 13 times. Gases have greater entropies than liquids, and that has greater entropies than solids. Guys, just stop for a minute. Enter into a Zen-like state. Next. And picture that. Please make that stick in your brain. Solids, liquids, and gases, right? Guys, which one has the most entropy? Gases. These are all spread out. Then liquids, then solids. Guys, you've got to get this. Again, 50% of you are going to miss this on the test, and I just got done telling you. Guys, this is critical. Liquids or gases are the highest, solids are the lowest, and then liquids are somewhere in between. Yeah. A perfect crystal at absolute 0. Well, so, and that's it. And the book talks more about this. So some of it depends on the scale that you're looking at. But at some point, they collapse on themselves. So if you have a crystal, a perfect crystal, no irregularities, no impurities. If you have a crystal, a perfect crystal, and if you cool that to absolute 0, entropy becomes 0. There's no disorder in the crystal itself because it's perfect and pure. And there's no disorder within the crystal structure because the molecules or the particles are not moving. If you can achieve that, you've achieved zero entropy. Is that okay? Well, and so then we need to talk, because these particles, and this gets a little weird, and I don't even pretend to understand it, but realize that what we're then talking about is the stuff that makes up the atoms, right? And now we're talking about protons, neutrons, and electrons. And you understand that when we talk about electrons, we're talking about probabilities. And those probabilities have entropy. So the electron clouds, by definition, have entropy because they're probabilities, and therefore there's always some disorder. The problem is that when we cool atoms down to close to absolute zero, the atoms themselves lose their identities. They actually become quantum packets that all start to look like each other, and entropy falls to zero because the atoms all become synonymous with each other. I'm pretty sure the first person that figured that out was pretty high on something, but it's actually the case that atoms actually lose their individual identities and therefore their entropy when they get supercooled. So it doesn't make sense when you're looking at a model, or oh, I just broke. More entropy. It doesn't make sense when you look at this, but if you're interested, look up something called Bose-Einstein condensates. And if we have some time at some point, I've got a really fascinating video on them where they actually describe this smearing of the wave packets that make up the atoms themselves. It's really interesting. Okay, so guys, you circled that 13 times, right? Then other things that you need to know about entropy go like this. If something is heavy, if something is complicated, or if something is long, it tends to have higher entropies. So again, guys, if it is heavy, complicated, or long, it tends to have higher entropies. Is that okay? Okay. So now, guys, let's start doing some math. So find this equation on your AP sheet. Delta S naught is equal to sigma delta S products minus sigma delta S reactants. Sounds familiar, right? It's very much like the equation that we looked at when we talked about Hess's law, when we talked about how to calculate delta H. But guys, please do this. Compare the delta H equation, which you are familiar with the delta S equation. First of all, you'll notice the ends are missing, right? That's fine. But guys, what is the glaring difference between the enthalpy change and the entropy change equations? Yes. Guys, let me repeat to you what Ronnie said. Notice in the enthalpy equation that it's delta H of products minus delta H of reactants. So those are heats of formation. Do you remember the logic behind it? We're breaking and forming bonds. And when we break and form bonds, we need to know the heats of formation. How much energy goes out when the products form? How much energy goes in when the reactants break down? That's enthalpy. Guys, when we talk about entropy, really what we do is this. How screwed up are the products? How screwed up are the reactants? And subtract the two. It's not how screwed up are the products when they form. It's how screwed up are they. And it's not how screwed up are the reactants when they form. It's how screwed up are they as they sit there. So entropy of products, entropy of reactants, subtract the two, and that gives us the entropy change for the reaction. It's really screwed up final minus screwed up initial. So guys, let's do it right here. It says this, calculate the delta S for the synthesis of ammonia from nitrogen and hydrogen. And guys, we're going to do this together. First thing we need is a balanced equation. Please write it. If you don't know, ammonia is NH3. That is something you should know, though. So, Oh, what do we need? We need a 2, and we need a 3. So now, guys, these solve almost exactly like the questions that we did in homework when we did Hess's law by computation. So it's got to be the same 4 lines. So delta S naught reaction is equal to the sum of N times the entropies of the products minus the sum of N times the entropies of the reactants. And again, guys, as Ronnie pointed out, these are not entropies of formation. They're entropies. How messed up are these things? So then, guys, we've got to craft this equation so that it fits our particular context. So our only product is NH3. So it's 2 times the entropy of NH3 minus the sum of the entropy of nitrogen plus 3 times the entropy of hydrogen. Is that right? I think that's right. That's right. So now, guys, we need the values. And that's why I had you open to page 801. So, guys, these are the standard molar entropies that are given right there in the and again, we could go to Appendix C, but thank goodness we don't need to. So what's the first one we need? NH3, where'd it go? 192.5. So we've got 2 times 192.5. Now, guys, let's talk. What are the units? Joules. Now, guys, pause for a minute and think about that. Think about all the numbers that you know for enthalpy values. Heat in, heat out. Guys, those numbers that we looked at in the homework that we just graded were also on the order of numbers that are in the range of 100, right? But guys, what are the units for our enthalpy values? Kilojoules. Guys, please understand the magnitude of this. Our enthalpy changes were thousands of times greater in energy than our entropy changes. Our enthalpy changes are in kilojoules. Our entropy changes are in joules per moles Kelvin. Much smaller values than minus, Max or somebody, can you give me the number for nitrogen? 191.5 joules per mole Kelvin plus 3, can you give me hydrogen? Say it again. 130.6 joules mole Kelvin. Guys, also notice this before we do the calculations. How many of those entropy values in that table, how many of those entropy values are negative? Why not? Yeah, you can't have negative screwed up. You can't be, hey, I'm better than perfect, right? You can't be negative screwed up. All of those values have got to be positive. There's no such thing as a negative entropy value. Although, guys, there's actually a group of physicists that actually think that they did achieve a temperature lower than absolute zero. And they did it by getting past zero entropy. Look it up. It's crazy. Again, I think these folks are high, but yeah. Maybe we'll look it up at the end of the day. Kelvin temperature below absolute zero. All right, so let's do the math. 192.5 times 2, and then 191.5, and then 3 times 130.6 0.6, add those together, subtract. I got negative 198. Is that right? So negative 198, and that's joules of energy. Now, guys, let's talk about the units. That's actually not them. It's joules, moles, Kelvin. I'm sorry, joules, Kelvin. Where did the moles go? They canceled. Because this is 2 moles, 1 mole, 3 moles. The moles cancel, and your units are joules, Kelvin. You guys okay? You're good? Okay. Gage, you okay? Oh, is it negative? Oh, it didn't get written down. Sorry. I could see the look in your eye going, wait, something's amiss. Yeah, sorry, I just forgot to write it down. So guys, what does that mean? It means disorder is going down. Disorder is going down. But guys, let's talk about why. This is a gas, this is a gas, and this is a gas. So guys, what is true of the entropy of these 3 things? They're all gases. They're all messed up. So why is this gas less messed up than those gases? Because there's less of it. Guys, over here we have 4 moles of screwed up. And over here we have 2 moles of screwed up. And 4 moles is more screwed up than 2 moles. Yeah. No. Oh, yes. In this particular calculation, yes. Yep. So your units will be joules Kelvin. You guys good? Okay. Then let's wrap this up. Okay. So guys, this is it. This is the end of chapter 19. Follow along. Here's where we're at. So, guys, we said at the very beginning of the day, the biggest idea in this entire unit, chapters 5 and 19, the biggest idea is a reaction spontaneous? And guys, we said that there's one and only one way to know. And the only way to know is Gibbs free energy. But guys, along the way, we've got to set the stage for this. So guys, this is where we are right now. Here's what we've said. All spontaneous reactions, I'm going to fudge this a little bit. You might want to write this in too. All spontaneous reactions tend to, that's better. All spontaneous reactions tend to, ... first of all, be exothermic. They give off heat. That's where we started the very beginning of the day. Logs burning, Bunsen burners burning, nails rusting. Guys, things that are spontaneous tend to give off heat. In addition to that, things that are spontaneous also tend to cause increases in entropy. But, guys, what if these things are in opposition, like a quick cold pack? What if we have a reaction that is not exothermic, but does cause an increase in entropy? Will that be spontaneous? And guys, this is where Gibbs free energy becomes very, very important. So guys, in order to predict spontaneity, we need to bring enthalpy and entropy together. And we do that into something called Gibbs free energy. Guys, Gibbs free energy is a thermodynamic function that combines enthalpy and entropy. Now, it's actually abbreviated G. Finally, an abbreviation that makes sense. But guys, the equation for Gibbs free energy is simply this. It is the enthalpy minus the temperature times the entropy. But guys, when we apply this to chemical systems, we now talk about changes. So the change in Gibbs free energy is equal to the change in enthalpy minus the temperature times the change in entropy. Find it on your equation sheet. Do you see it there? You're good? Okay. So guys, now we're ready to answer the question, is a reaction spontaneous? And guys, it goes like this. The way to know if a reaction is spontaneous is only based on its Gibbs free energy change value, and it's this simple. If delta G is negative, that bugger's spontaneous. But what if it's not negative? Well, guys, if delta G is 0, it's at equilibrium. Huh? But now, guys, what if delta G is positive? Here's what that means. If delta G is positive, the reaction itself is not spontaneous, but the opposite reaction is. The opposite reaction is. And that's an important point that we'll talk about more in just a minute. You okay? Can we go on? Okay. So guys, now look back at your AP equation sheet. We can also quantify Gibbs free energy with this equation. That we can actually look up Gibbs free energy changes of formation for products minus reactants, and we can do some math. But along the way, guys, we always have our eye on this idea. Any spontaneous process will always cause a decrease in Gibbs free energy. Delta G is negative. So guys, fundamentally what that means is this. If we have a reaction, and if the Gibbs, wrong page. If we have a reaction, guys, and delta G is less than 0, if it's negative, then the reaction favors products. So a negative delta G means that the reaction is spontaneous, is written, it moves to the right, and it goes to products. If we have a delta G that's positive, it means the reaction's going in the other direction, and it favors reactants. Does that sit okay? So guys, this then is the moment where we now answer the big question. You ready to go? Okay, do this. Change the page in your book. To page 809. So guys, what's the big idea? Is a reaction spontaneous? But guys, now what we're going to do is we are going to expand the question. Join me at the board and let's do this. And guys, this is where the AP authors are going to get you. So guys, it goes like this. So the big question that they are going to get you with is not if a reaction is spontaneous, it's when is a reaction spontaneous. So guys, follow along with the logic. Don't look at your notes. Join me. Guys, this is the way that this works. The question that you've got to be able to answer is if and when is a reaction spontaneous. So guys, it goes like this. Looking at this equation, we have three factors. We have free energy, we have enthalpy, and then we've got this term over here, which is our entropy term. It's minus temperature times the change in entropy. Now guys, this is the way to organize your thinking around this. So we've got an enthalpy term and we've got an entropy term. And let's pull this together. So guys, our big question is a reaction spontaneous? So guys, what delta G values tell us a reaction is spontaneous? Negative? Is that okay? So guys, a negative delta G value tells us that a reaction is spontaneous. So let's do this. And you can write this down with me if you want. Is spontaneous and isn't spontaneous. So a negative delta G value is spontaneous. A positive delta G value is not spontaneous. Now, guys, let's have the same conversation for enthalpy. Think through this with me logically first. Endo or exothermic? Which reactions tend to be spontaneous? Yes? Exo? Okay. Guys, what sign means exothermic for enthalpy? Negative or positive? Negative. So negative enthalpy values are spontaneous. What about positive values? Not spontaneous. Again, is and isn't spontaneous. So negative enthalpy, that's exothermic, is spontaneous. Positive enthalpy, endothermic, not spontaneous. Now, guys, let's talk about entropy, disorder. Which one tends to be spontaneous? Disorder up or disorder down? Which one tends to be spontaneous? Disorder up or disorder down? Disorder up. So, guys, positive delta S values tend to be spontaneous. Negative delta S values do not. So now, guys, we've got to do some math. Follow along with me and this will make sense. Ready? Here's the idea. Are you all in agreement that negative delta G is spontaneous? Now, guys, watch this. If enthalpy is negative, that would tend to make this negative, right? So that lines up. If this is exothermic, that's negative. That tends to make delta G negative. But now, guys, do this. If this is positive, that tends to make a reaction spontaneous. But how does positive this tend to make negative that? Do you see it? Guys, what does this temperature always have to be if it's Kelvin? It's always got to be positive. There's no such thing as a negative Kelvin temperature. So, guys, temperature has always got to be positive. So look at what we've got. A positive times a positive times a negative makes the value negative. Get it? Now, guys, watch this. Let's look at the other side. What if delta G is positive? That works against spontaneity, right? But so does endothermic. But so does a decrease in entropy. But if this is negative and this is positive, and if this is negative, a negative times a positive times a negative makes all of this positive, which makes that positive, and that works against spontaneity. Do you see how the signs line up? Does that make sense? Okay. Now, guys, do this. Let's go here and let's pull this together in this table. So, guys, do this with me. You can do it in your notes, or you'll notice that it's also in the book as well. But, guys, we're going to play with this. Ready? Start with me here. Check this out. Delta H is negative. Does that tend to be spontaneous? What does negative delta H mean? Exothermic. Tends to be spontaneous, right? Positive delta S. Does that tend to be spontaneous? Also, yes, disorder is going up. So, guys, look at the result. If that's the case, then delta G will always be negative, and this will be spontaneous at all temperatures. Get it? Now, guys, what about this? What if delta H is positive? Does that favor spontaneity if delta H is positive? No, that's endothermic. Now, guys, what if delta S is negative? Does that favor spontaneity? No, disorder's going down. And guys, if that's the case, delta G is always positive. And that means, guys, that this reaction is non-spontaneous at all temperatures. But the reverse reaction is spontaneous. Just keep that in mind. Now, guys, what about this? Don't miss this, because this is the thing they're going to get you on the test. Guys, negative delta H, does that favor spontaneity? Negative delta H, yes or no? Yeah, exothermic. Negative delta S, does that favor spontaneity? No. So let's take these ideas up here. Negative delta H does favor spontaneity. Negative delta S does not. So guys, if we want this reaction to be spontaneous, what do we have to do? And the answer is we need to decrease the influence of the thing that is fighting against spontaneity. So guys, our entropy term is fighting against spontaneity. So how do we decrease the impact of that? We make the temperature go down. And if the temperature goes down, then the value of this term decreases, making it more likely that the reaction can be spontaneous. So guys, here's the idea. If both of these are negative, then this reaction is spontaneous at low temperature and becomes non-spontaneous at high temperature. Does that make sense? Now guys, let's do that again. What if we have a positive delta H? Does that favor spontaneity? It does not. What if we have a positive delta S? Does that favor spontaneity? It does. So now, guys, we've got the opposite scenario. Now, let me clean up my mess. Now, guys, what we've got is this. We've got a positive delta H, and that does not favor spontaneity. We've got a positive delta S, and that does favor spontaneity. So how do we get this reaction to be spontaneous? Well, we got to make this bigger. And how do we make this bigger? We heat it up. So guys, that reaction becomes spontaneous at high temperature because it's the entropy term that does favor spontaneity. Do you understand the logic behind that? Guys, that's huge in this unit. You've got to be able to think through how entropy and enthalpy changes come together with temperature changes to influence spontaneity. Anything there you want to talk about? Okay, we got one more question to go, guys, and we're done for the day. But let me turn it to you as a question. Guys, given this entire conversation that we just had, especially relative to these examples down here, what's the question that it leaves you with? Become spontaneous at high temperature. Become spontaneous at low temperature. What haven't we talked about? Yeah, where's the divide? What is high? Higher than what? Lower than what? Guys, we understand that it's high and low, but higher or lower than what? And guys, that's what we need to define, and we're going to do this last. And guys, there is not a place for this in your notes, so maybe flip your paper over and let's talk. You just need, and you want to write this down. Guys, this you will see on the test next time. Let's take a fictitious reaction where A and B become C and D. And delta H and delta S let's say that delta H is 100 kilojoules per mole, and that delta S is 25 joules per mole Kelvin. And by the way, guys, I didn't include the signs. Both of these are positive. Y'all caught up? Guys, question number 1 is this. Is this reaction spontaneous at all temperatures? Is it non-spontaneous at all temperatures? Or is it spontaneous at high temperature or low temperature? All, none, high, or low. Please write down your thoughts. All, none, high, or low. Commit to an answer. All, none, high, or low. So guys, rather than call you out on it, let's talk about it. So how do we think about this? So guys, in order to think about this, here's what we need to do. Positive delta H, does that favor spontaneity? No. So here, let's do this. All, none, high, low. So guys, positive delta H does not favor spontaneity. That means that all is not the answer, because delta H does not favor spontaneity. Now guys, what about a positive delta S? Does that favor spontaneity? It does. That means none is not the answer, because we've got at least one factor that does favor spontaneity. Guys, what would none look like? It would be positive negative, right? So now we need to know whether it's high or low. Guys, to distinguish that, we can take our equation, delta G is equal to delta H minus T delta S. So guys, which of our factors, H or S, delta H or delta S, favors spontaneity? Well, it's delta S. So this is the thing that favors spontaneity. So if we want this reaction to be spontaneous, we want to amplify the impact of that factor, and we do that by doing what to temperature? Increasing it. So guys, the answer is high temperature. Questions on that? So now, gang, the question is higher than what? So let's do the math. Do this with me. Higher than what? Well, guys, we're solving for temperature. Our delta H is 100 kilojoules per mole. Do this with me. Now, T is our variable we're solving for. Minus T. And now we need our value for delta S. Why is the value for delta S not 25? It's in joules. And guys, we have got to convert it. Now watch. You can convert kilojoules to joules if you want by multiplying by 1,000. But guys, I hate dealing with numbers like 100,000. So it's easier for me to convert joules to kilojoules by dividing by 1,000, and that makes this 0.025 kilojoules per mole Kelvin. But guys, now we've got a problem. We're trying to solve for T, but we still have another variable we don't have a value for. delta G. So what do we do with delta G to solve this for T? Set it equal to 0. What does that mean? What happens when delta G is 0? That's at equilibrium. And so guys, if you think about it, the tipping point between spontaneous and not spontaneous is equilibrium. So what we do is we set this equal to 0 and we solve. But the temperature that we're going to get will then be the temperature of equilibrium. So to solve this, by the way, guys, our kilojoules drop, our moles drop, and when we do the math as we divide, Kelvin jumps on top. Our answer will be in Kelvin. So we have negative 100 is equal to negative 0.025 T, or 100 divided by 0.025. And guys, temperature is 4,000 Kelvin. But that is not the answer to the question. Because the question is, at what temperature will this reaction be spontaneous? What's the answer? Any temperature greater than 4,000 K. Guys, when you've got to identify that as a sentence. And you're going to, I get this all the time on the test too. If you write down that this reaction will be spontaneous at 4,000 Kelvin and above, that's wrong. It's not spontaneous at 4,000. It's at equilibrium. So the way to say this is the reaction will be spontaneous at any temperature above 4,000 Kelvin. Do you see the difference? Okay. So guys, we now have 15 minutes left, and we are done. So let me clean this up. Looks like this. Here's your homework. And guys, I know that for some of you, it feels like you're just being thrown into the abyss. You're going to go home tonight. You've got a lot of homework to do. The answers are posted on our website, but you need more support maybe. And you're going, wait, I don't get to come back to campus for days. What do I do? Guys, please take advantage of GroupMe. If you have questions, understand the A through K kids are working on this too. You could access them. But guys, I'm available too. I'm here every day after school except for Friday. Please, if you want to get together, let me know. But you have to let me know. We will still be social distancing. But man, if we just want to order pizza and study, as long as we don't touch each other's pizza, we're good. So guys, I would love to be available to you. If you are going to do study groups outside of school, that's great. But guys, please, as much as you can, be careful. But I encourage that as well. And then guys, again, when I see you on Tuesday, we will have ample time to answer homework questions. So it's not going to be like you're going to walk in the door, the bell rings, and let's get to work. We can ease into the test on Tuesday, so we'll have that time as well. So, guys, any other questions that should get recorded in the screencast? You guys good? Okay, so I'm going to stop recording. Guys,